And thank you for being here, Lamont. We really appreciate it. And I'm really excited to hear about how you are working to bring together general relativity and quantum mechanics.
Well, I appreciate that. So thank you. So thank you very much. I appreciate that. I appreciate your interest in this. Um, and I want to say hello to everyone. First I want to thank the Monterey Friends of CGUN for having me. I applaud the Society for providing a forum to shed light on new ideas. It's really important. So I applaud the work that you're doing. So my talk today is on the fundamental aspects of the universe, namely space, time, matter, energy, and the main theories that describe them. You may have heard of these. They're called general relativity and quantum mechanics. I'm going to focus particularly on the concept of time and show that it can connect those theories and thus various aspects of the universe. There are many, let's see. There we go. There are many ideas that I hope you walk away with tonight, but chief among them is the idea that time itself has energy, and indeed it is the greatest source of energy in the universe. At the onset, I'd like to stress that the issues of space, time, matter, and energy should not be regarded as being of mere academic interest. We've all likely heard of the saying, don't keep all of your eggs in one basket, but for right now, that is the case with humanity. Understanding space, time, matter, and energy is important, not only for our long-term success, but also for our long-term survival. It is critical that we eventually become a multiplanetary interstellar species, but we'll never get there without understanding fundamental aspects of the universe better. Also, there's an interesting connection between the concepts I'll discuss and human thought. I will highlight that as well in the spirit of Yoon's work. A little housekeeping. In the interest of time, unfortunately, I had to leave some details out. So depending on your level of knowledge with the concepts I'll be discussing, if you feel something, if you feel I've left something out, I likely have an explanation for it, but just didn't necessarily include it here. But I'll be happy to answer questions if you'd like to connect here or after the session. So I'm going to at times refer to my work, and by that I mean temporal energy theory. This is the idea that time itself has energy. I outlined this concept in the book, The Greatest Source of Energy, A New Theory of Time. I'll skip my introduction since we really just went through that, and I'll just jump right into it. So there are two great theories describing the universe, general relativity and quantum mechanics. General relativity describes the behavior of big things like planets, stars, and galaxies, while quantum mechanics describes the behavior of small things like electrons, protons, and atoms. So far, scientists have endeavored to combine general relativity and quantum mechanics into a single framework they call the theory of everything. What they mean by the theory of everything is that if you had one theory that incorporated both general relativity and quantum mechanics, you would have a single rule book that described all fundamental physical phenomena. However, they have not been able to accomplish this. So what's the problem? The problem is they work well together, but they work well separately, but not together. When you try to add general relativity and quantum mechanics together, you appear to get an error in the math, and that error concerns time. Specifically, you get an equation called the Willard-Dewitt equation that basically says there is no time in the universe. But time plays a crucial role in both general relativity and quantum mechanics. They cannot work without time. So an equation that says there is no time when you try to combine the two theories seems problematic. So how do we solve this problem? Well, we need to better understand time. So then what is time? This question has been asked for centuries. The great theologian and philosopher St. Augustine, who lived around the 4th and 5th centuries AD, is famous for a statement about time. It goes something like this. He asks, what is time then? If no one asks me, I know. But if I were desirous to explain it to one that should ask me, plainly, I know not. So basically he's saying, if you don't ask me, I know what time is. But if you were to force me to try to explain it to you, I can't. Isaac Newton and Albert Einstein had very profound thoughts on time that have persisted to this day. However, their thoughts on the subject could not be more different. For Isaac Newton, time is universal. It ticks away regularly for everybody. But Einstein says, no, time is not universal, it's relative. It does not necessarily tick at the same rate for everyone. Newton says that time exists as a separate background clock on the static stage of space. But Einstein says, no, time and space are linked, forming a four-dimensional stage called space-time that is not static, but dynamic. Time being relative means that it may tick at different rates for different people. The rate at which it ticks has to do with how far or close you are to a gravitational source, such as the Earth. Using this mountain as an example, time ticks more quickly at the top of the mountain than it does at the bottom, which is closer to the surface of the Earth. Each place that ticks differently across the mountain is what we call a separate reference frame. For folks at a particular in a particular reference frame, here either 1, 2, or 3, time seems to tick normally for them, not fast or slow. But to those in reference frame 1 at the top of the mountain, those in reference frame 3 are moving more slowly. That is, their time seems to run slower. The clocks presented in the diagram here are exaggerated just to show the effects clearly. Space-time being dynamic means that it can be bent, stretched, or compressed. In this picture, Earth is bending the space-time around it. Another object within the curved area will move along the curves toward Earth, and this generally is how gravity works in general relativity. A famous quote by noted physicist John Wheeler is that matter tells space-time how to curve, and space-time tells matter how to move. And here's just that representation with the Earth and the Moon. So quantum mechanics uses the time of Newton. General relativity uses the time of Einstein. But again, when you try to combine general relativity and quantum mechanics, time appears to vanish or short circuit in the math. So how do we solve this problem? In my book, The Greatest Source of Energy, A New Theory of Time, I provide a way for possibly joining these two works. I do it through what, again, I call temporal energy theory, which, as the name suggests, is a concept in which time has energy. I would not go so far as to say my work is a theory of everything, but I believe it does provide a roadmap for getting there. So temporal energy theory, I believe, can help us answer not only the question of what is time, but actually several other questions, such as why is there more matter in the universe than antimatter? What is the nature of electric charge? How is time relative and as described by Einstein, and universal as described by Newton? How are the four fundamental forces of the universe united? And together with the previous question about the relative or universal nature of time, those two questions really get at the heart of combining general relativity and quantum mechanics. Also, I believe temporal energy theory can help us understand the nature of dark matter and dark energy, the nature of mass. And again, we can explore if it can help us to find a way that we can potentially become a multiplanetary interstellar species. And as I said earlier, there is an interesting connection to thought and self-awareness that I will also talk about. So the new concept of time, temporal energy theory. So in temporal energy theory, time can be considered as a four-layered concept. Time as a field of energy within space, adding another dimension to that space. Time as a particle. Time as a basic bidirectional process. And time as a thermodynamic unidirectional process. The best way to think about it is to think of an air-filled balloon. You can think of the balloon itself as space and the air within the balloon as time. That is, in the same way that the air within the balloon behaves like an energy field and adds another dimension to that structure, time as an energy field adds another dimension to space. So you have an air-filled balloon or time-filled space called spacetime. But I want to emphasize here that I'm talking about the structure of spacetime itself, not about a substance in spacetime. Now, as we all know, an air-filled balloon can be stretched and compressed and curved, and this is true of space-time also, as Einstein has showed us. Space-time is dynamic. It too can be stretched, compressed, and curved, as I mentioned. So the analogy holds up. Now, the air within the balloon can be broken down into particles, which in this case are called molecules. And I know air is a mixture, but for the sake of simplicity, let's just focus on oxygen molecules. In a similar way, time can be broken down into particles in my work. I call the particle of time that composes this time dimension a T+ particle. These particles are extremely small. I'm talking something like 10 to the power of 22 times smaller than an electron, for example. Now imagine in our air-filled balloon, let's say there's an ant, and she is reclining in a chair reading a book, munching on some potato chips, and beside her is a potted plant. Now, as the ant breathes in the oxygen in the oxygen-filled balloon, she is expelling carbon dioxide. As the ant breathes in the oxygen, she's expelling carbon dioxide. Now, the plant is taking in the carbon dioxide and expelling oxygen. So there's a cycle. Now, let's look at our space-time scenario. Instead of the ant and a potted plant, I'm going to say there are two particles, an electron, which has negative electric charge, and a positron, which has positive electric charge. For now, and I know these particles normally annihilate one another, but for now, I'm going to ignore the fact that they annihilate and just let them sit there for a moment. So in this scenario, the electron and the positron are just sitting near each other, not annihilating just yet. So the electron is equivalent to the ant, and the positron is equivalent to the potted plant. As the ant breathes in oxygen, the electron, in a sense, breathes in or interacts with the T plus particle that is composing the volume of time within our space. As the ant expels CO2, the electron, in a sense, expels a T minus particle. So then as the plant takes up the CO2 and expels an oxygen, the positron will take up the T minus particle from the electron and expel a T plus particle. So there's a cycle there. This cycle is what I refer to as basic time. This is time on a particle level. This is time that can go in either direction. For the electron, time seems to be ticking in the positive direction as it takes in T plus and expels T minus. And the positron looks like it is ticking in the opposite direction as it takes in T minus and expels T plus. You can think of them as having oppositely running clocks. If the electron's clock is running clockwise, the positron's clock is running counterclockwise because it is doing the opposite process. So you might ask which clock is the correct clock, which one has the right time, but actually each time process is legitimate. The T plus to T minus process of the electron is just as legitimate as the T minus to T plus process of the positron. Now the matter in our universe is composed of electrons, not positrons. Electrons are one aspect of the matter that composes our universe. We live in what is called a matter-dominant universe. Positrons are an example of antimatter. So our time in this universe being composed of matter, our time is the T plus to T minus process. However, if you had a universe that was composed of antimatter, you would have a universe that worked just like ours. The stars would shine, the birds would chirp, everything would work the same, except that the time would be running in the opposite direction. Now, looking back at our ant, as she's eating and metabolizing her potato chips using the carbohydrates to produce energy within her body, she's giving off heat in the form of photons. Those photons are emanating from the ant in the form of heat. Those photons that are emanating from the ant in the form of heat are only going to flow in one direction, that is away from her into the greater volume of the balloon, never to spontaneously return. That is, the photons are never going to return and the whole process run backwards to get a potato chip again. Metabolism of food is a one-way process. This is the thermodynamic arrow of time. This is time that moves in a single direction. This is related to the aging process, the fading of paint, the cracking of an egg, and the metabolism of food. Looking back at the electron and positron, if they have enough energy, they can wiggle and jiggle and radiate photons away from themselves. These photons, again, move in one direction away from the particles. They would never return to the particles. It's a one-way operation. Note that the thermodynamic arrow of time runs in the same direction for both the electron and the positron, for both matter and antimatter. This is different from basic time, which flowed in opposite directions for the electron and positron. Now, I'd like to emphasize that all of these forms of time are related to one another. First, you have the time dimension. You drill down and you have a time particle. that time particle helped the electron to, in a sense, breathe. The electron interacts with the T plus particle and expels T minus particle as the ant breathed in the oxygen and expelled carbon dioxide. This gives the electron energy, allowing it to wiggle and jiggle, if you will, and in so doing radiate photons that move away from it in one direction, never to spontaneously return, giving rise to a thermodynamic unidirectional arrow of time. Now let's say, instead of a universe filled with T plus, let's say our universe were instead filled with T minus. If this were the case, the electron in this case would, in a sense, suffocate in the same way that I would suffocate if I were in a space filled with only carbon dioxide. In this case, I believe the electron would decay into what's called an electron neutrino and thus lose its electric charge. Now I'm leading to something here because remember I said that the positron is sitting there, but the volume of space was filled with T plus. And I said if it were filled with T minus particles, the electron would suffocate and decay. So does that mean the positron suffocates and decays in a T plus filled space? And the answer is yes. I believe that the electron, the positron will decay into what is called an anti-electron neutrino because it cannot breathe the T plus atmosphere of our universe. And this is what I believe gives an advantage to matter and leads to the predominance of matter in our universe. So starting from the beginning, when the universe was first created, there were equal amounts of matter and antimatter. And for the most part, they just annihilate one another and form photons. But because our universe is filled with T plus, matter particles such as electrons thrive. A positron that did not annihilate with an electron will in time suffocate, which is to say decay into an anti-electron neutrino. So then you might ask, well, where is the T minus particle that the electron is giving off? Where is it going? In my opinion, is that for the most part, it's leaving our space and going into a parallel space. So some of you might have heard of this concept of parallel universes. I do believe there is one parallel space. But when I say parallel space, I really mean that in the most generic sense possible. I'm saying that I'm not saying that there are anti-people and anti-plants or whatever. It's not space that anything could live in. All it is basically is one big positron or one big positive electric field, which appears to have negative energy because it is associated with T minus particles. As such, it is equivalent to the negative energy vacuum of quantum mechanics, which exists in that theory to prevent electrons from taking on negative energy. Which in my work simply means preventing it from being surrounded by T minus particles. So I call the space we live in interior space and the parallel space exterior space. These are just labels. I call interior space interior because we living in that space see the interior of it, and the parallel space is external to our experience. So I call it exterior space. But again, these are just labels. So a T minus particle enters the parallel space, is converted to a T plus particle, and is ejected back into our space where the cycle continues. I believe the reason exterior space is positive is because the space we exist in used to be negative. It just turned off. I'm going to use the concept of blue and yellow make green to explain this. Again, these are just labels. There's nothing really blue or yellow or green, but the colors are useful to illustrate. Now, in temporal energy theory, the universe began as a small dot-like field of green or electrically neutral space that polarized into its blue and yellow natures, with blue representing negative charge and yellow representing positive charge. The blue side is interior space, the space we live in today, and the yellow side is exterior space. It is this polarization that I refer to as the Big Bang. Interior space is blue and thus has negative charge. It is basically like one large electron, and it's filled with T plus particles. Exterior space is yellow and thus has positive charge. It is basically like one large positron, which I mentioned before, and is filled with T minus particles. Being like an electron, the blue space will transform T plus to T minus. Being like a positron, the yellow space will transform T minus to T plus. This causes an instability because the blue space is trying to eject T minus into the yellow space, while simultaneously yellow space is trying to eject T plus into the blue space. It is like a crowd of people in two adjoining rooms, with one crowd trying to get into room A at the same time the other crowd is trying to get into room B. This instability causes space to expand rapidly. The instability continues until one of the spaces, in a sense, gives in. And what I mean by that is that it turns green. Which one does is completely random. Here, blue space has turned green, while yellow space has retained its positive charge. In turning green, the blue space is no longer repelling the T minus within it, in a sense, taking a step back from that doorway where everybody's trying to get through at the same time. So in turning green, blue space now has in a sense taken a step back from the doorway, allowing the yellow space to eject its T plus, with yellow space subsequently pulling in the T minus of green space, leaving green space ultimately filled with T plus. The original blue nature of interior space then comes through as blue particles, meaning matter particles like electrons, particles that can process time in the T plus to T minus direction, as all of blue space used to be able to do before it turned green. And this process continues. And this process continues with the electron transforming T plus into T minus, the T minus being pulled into yellow space, that space converting it back to T plus and ejecting it back into green space, and the cycle continuing. As such, in my work, this temporal polarization, this polarization in time is the foundation of electric charge. When a space or particle is polarized in the T plus to T minus direction, that is equivalent to having negative charge. If it is polarized in the T minus to T plus direction, it has positive charge. Here, I have a slice of green space on the left. If an electron were placed within this space-time, it would polarize the space-time surrounding it, creating alternating blue and yellow segments radiating away from it. A static polarized segment of space-time emanating from a charged particle is what I describe as a virtual photon, a particle of light. When it gains more energy, forming a wave within the field, it forms a real photon. Each blue and yellow element, as well as the blue and yellow pairs, are individual packets of energy or quanta of energy. A field of virtual photons creates an electrostatic field. And if a real photon had enough energy, it can give rise to an electron-positron pair. Now, an electron will polarize space beginning with blue and then yellow thereafter, while a positron will do the opposite, polarizing space-time beginning with yellow and then blue thereafter. Now, here I'd like to note that in life, there are a few absolutes, and so there is some T minus in interior space, I believe. It is just that there's not a lot of it. All positrons will not spontaneously degrade, but matter still has a significant advantage over antimatter in our space, which contains mostly T plus energy. Now, in electric attraction, the field lines meet, merge, and collapse, pulling the particles together. Here, I just show an electron and positron annihilating one another, sending blue and yellow waves of space-time off in opposite directions. In electric repulsion, here with two electrons, the field lines are unable to merge and instead bounce off of one another, pushing the particles apart. With that said, if we could return for a moment to the beginning of the universe as described in my work, one can see that the Big Bang moment led to a condition in which the universe itself resembled a particle of light, where the blue and yellow resembles, the blue and yellow space resembles a photon, quite literally. So one can argue that the Big Bang, really was a let there be light moment. which I thought was interesting given some religious creation stories. It is not that light is created in our space, that blue, soon to be green space. It is that the whole universe resembled a particle of light. If we want to review for a moment, I aim to answer several questions. One is, what is time? So I said that time is a four-layered concept, a dimension or field of energy, a particle that you find when you drill down into that energy field, like finding an oxygen molecule when you drill down into a volume of air. Time as a basic bidirectional process, and time as a thermodynamic unidirectional process. I explained that there is more matter in our universe than antimatter, because matter can, in a sense, breathe the T plus atmosphere of our space, while antimatter cannot. I explained that electric charge is the temporal polarization of space-time or a particle, in which negative charge is associated with T plus to T minus time, and positive charge is associated with T minus to T plus time. Now, I'd like to address the question of whether time is relative, as Einstein says, or universal, as Newton says. Now, in our space-time, every electron, every particle of matter is its own clock. Being matter, they all process time in the T plus to T minus direction, as explained. However, the rate by which they do so may vary. Recall that Einstein showed us that time will tick more slowly closer to a gravitating body, such that when you were at the bottom of a mountain, time will tick more slowly than it would if you were at the top of the mountain, with the different areas of time being different reference frames. In temporal energy theory, temporal particles are attracted to all forms of energy, condensing around the source of energy, with the densest layer of temporal particles closest to the object, with the density tapering off as you move away from it. I believe these different temporal particle densities are what give rise to Einstein's reference frames. If you place the mountain over top of the image with the different temporal particle density layers, you would see that different sections of the mountain overlay different density layers. Here is a zoomed in here is a zoomed in view of that, where the vertical black lines represent different densities of temporal particles. Thus, again, the different temporal particle densities are associated with with Einstein's different reference frames. We can use one electron from each of the mountain layers to look at what's happening at the level of basic time. The electron at the bottom of the mountain might, at the bottom of the mountain, might have, as an example, only 3 T plus to 3 T minus cycles per fundamental moment of time. Whereas the electron in the middle might have 6 T plus to T minus cycles, and the electron at the top might have 12 T plus to T minus cycles per moment, per fundamental moment. The rate of time, the rate of basic time is associated with the rate of thermodynamic time. The fewer cycles there are, the fewer basic cycles there are, the slower thermodynamic time will move. 3 T plus to T minus cycles would be associated with slower aging, metabolism, etc., whereas 12 T plus to T minus cycles would be associated with faster processes. Collectively, the 3 electrons produce 21 T minus particles, which enter exterior space, are converted to T plus, and are ejected back into interior space. And exterior space is doing this for all matter particles in our space simultaneously. It is taking in all of the T minus particles for all of the matter in our universe per cycle. Thus, exterior space behaves like one clock that ticks at one rate for all of interior space. Exterior space thus is the universal background clock. The time of exterior space, however, is unknowable to us in our space. To know the true time of exterior space, one would have to step outside of the entire universe and look back at it, which is impossible. Thus, we can never know the time of the universal clock. All we can discern from it are the energy changes that come from it through the lens of our relative time. On the other hand, Interior space has many clocks, some that tick at different rates. And matter particles can only tell time through their lens. Time for them is relative to which reference frame they are in. So thus, with this being said, both Newton and Einstein are right. Time is universal and relative. This is because there are two codominant temporal processes occurring in the universe. The many clocks that are the matter particles that all tick in the t plus to t minus direction, perhaps at different rates, but that all tick in the t plus to t minus direction. And the one clock of exterior space that ticks in the t minus to t plus direction. So again, Newton and Einstein are both right, which is a significant point because until now, scientists thought that they could not be both right at the same time. So with that, I'd like to discuss how the fundamental forces of the universe can be united, because this, along with the question of is time relative or universal, really gets at the heart of combining general relativity and quantum mechanics. So I'll start with gravity. In general relativity, gravity is said to be caused by the curvature of space-time. As noted earlier, matter tells space-time how to curve, and space-time tells matter how to move. This is a quote from John Willard. It is the latter statement that we need to focus on. Often in demonstrating general relativity's description of gravitational attraction, an individual will place a marble onto a flexible sheet. The marble here is painted like Earth, causes the sheet to bend. If another ball is placed onto the vicinity of the curve in the sheet, it will roll toward the larger ball. This is to demonstrate that the curvature of the sheet, here representing space-time, is what causes gravitational attraction. This is similar to my work, if you recall, that temporal particles swarm and condense around sources of energy. In so doing, they form curved layers of time around those sources. Here represented as just concentric layers of time. And as they flow toward the sources, they also curve and compress the space around those sources. In the diagram on the right, the arrows are representing the flow of temporal particles toward an object. Let's call it a planet. The sort of half circles around the planet represent the curvature and compression of space due to the flow of the temporal particles toward the planet. This is similar to the scenario with the flexible sheet. The diagram on the left represents that condition where, again, the object curves the sheet as it is placed onto it. The diagram in the middle shows a similar situation, but in a sense with the sheet folding around the object. They look similar, but differ in cause and effect. In the middle diagram, the curvature is occurring because time is flowing toward the object. The diagram on the right is just the same as that in the middle, but turned on its side. However, not only is the diagram on the left using gravity to describe gravity, right? You put a ball down and it drops, but you're using gravity to describe gravity. It also leaves some people with the impression that general relativity is saying the curvature of space is responsible for gravity, when really it is saying the curvature of time is responsible for gravity. Here's a quote by William Reuters. So he says, many experts in general relativity, including Einstein himself, have emphasized that everyday gravity is explained by the distortion of the temporal part of space-time geometry rather than the spatial part. And this is Einstein also mentioned the importance of time in causing gravity in his book, The Meaning of Relativity. William Unruss said, it is not that there are two separate phenomena, namely gravity and time, and that one, gravity, affects the other. Rather, the theory states that the phenomenon we usually ascribe to gravity are actually caused by times flowing unequably from place to place. Now, in my work, of course, that this is literally the flow of temporal particles toward matter, that unequable flow. In this diagram, you can consider, and here I'm going to consider two particles in space. You can consider them planets, and we can call them planets 1 and 2. Now, between them, thus, would be a common field of T plus particles. As with all matter, they would process time in the T plus to T minus direction. In so doing, they would be competing for the temporal particles in the common field between them. Some of the temporal particles flow toward planet 1 and some to planet 2, and a tension builds within the temporal field because temporal particles are sticky. They're sticky particles. Eventually, the two planets will start to move toward one another as they consume the field of temporal particles between them. This is temporal energy theory's interpretation of what is really happening under the surface in general relativity. I'm suggesting that some interpretations of general relativity are confusing cause and effect. The curvature of space-time does not cause gravity. Space and time are curved where gravity is occurring, where gravity is the movement of T plus particles toward and around matter, that unequable flow of time from place to place. The conversion of T plus to T minus by matter and the loss of T minus to exterior space, where space is curved simply as a consequence of this activity. Thus, if time is curved, space is curved. If space is curved, time is curved. But spatial curves do not cause gravity. Temporal curves do. Gravity, in other words, is caused by the curvature or flow of time. One of the key points here is that from an energy perspective, gravity is caused by the removal of T plus particles within the common field between two gravitating bodies. This is consistent with the fact that when matter is coupled to a gravitational field in general relativity, the matter energy is said to be counterbalanced by gravitational energy such that the total energy is zero or vanishes. Returning to a previous diagram, this zeroing out or vanishing of energy is equivalent in my work to the flow of T plus particles toward matter being counterbalanced by the T minus particle moving away from it. T plus T minus is zero. That vanishing of energy, but mathematically, but in physically, the T minus is leaving our space and entering exterior space, as I explained. But again, I want to stress that from an energy perspective, gravity is caused by the removal of T plus particles within the common field between two gravitating bodies in my work. This is particularly important as we discuss the other three fundamental forces, namely electromagnetism, the weak nuclear force, and the strong nuclear force. So let's do that. So electromagnetism involves the interaction between electrically charged particles and the interaction between the poles of magnets. The weak nuclear force involves neutrino interactions and radioactive decay, and the strong nuclear force holds elementary particles called quarks together to form protons and neutrons, which are at the center of atoms, the atomic nucleus. Now, these forces are said to be caused by the exchange of virtual particles. So electrons would be undergoing the force of electromagnetism through the exchange of virtual photons, which we kind of discussed earlier. Electron neutrinos would be undergoing the weak force through the exchange of virtual Z bosons. And quarks would be undergoing the strong force through the exchange of virtual gluons. These are just names of different particles. In quantum mechanics, particles must borrow energy from the vacuum to create these virtual particles and thereby engage in the various forces, and they must pay that energy back quickly. In my work, that borrowing of energy from the vacuum is equivalent to the borrowing of T plus from the vacuum and the electron taking it up. Recall that I stated that if an electron were in a space filled with T minus, it would suffocate, decaying into electron neutrinos, thereby losing its electric charge. I'd like to add to that by adding that even a neutrino would decay further if there were still not enough T plus particles in the space. It would decay into what I believe is a sterile neutrino and be unable to engage even in the weak force. So basically, all of the particles involved in these forces require an influx of T plus particles. The electrons require an influx of T plus particles to maintain their charge and engage in the electromagnetic force. So they wouldn't suffocate, right? So they wouldn't suffocate and lose their charge. Same thing, neutrinos require an influx of T plus particles to engage in the weak nuclear force. Quarks need an influx of T plus particles to engage in the strong force. If they didn't have that steady influx, they would, in a sense, suffocate, decay, and not be able to engage in these forces. So they need that steady influx of temporal particles to engage in those forces, and that is my equivalent of that quote unquote borrowing of energy that is required in quantum mechanics. So a key point here is that from an energy perspective, electromagnetism and the weak and strong nuclear forces are caused by the addition of T plus particles by matter. So if we want to compare general relativity and the other forces side by side, we can see that gravity is associated with the removal of T plus particles, whereas electromagnetism and the nuclear forces are associated with the addition of T plus particles. This helps to illustrate the fact that energy really is not conserved at the local level in general relativity or quantum mechanics. General relativity is associated with a loss of energy, and quantum mechanics is associated with a gain in energy. As you might remember, we were taught in school that energy cannot be created or destroyed, but looking at these theories separately, one might come to that conclusion. The loss of energy in general relativity is generally not discussed head on. At most, it might be said that that there is no good local characterization of energy in general relativity. However, in the setting of gravitational redshifting, where light radiating away from a planet loses energy, one is forced to conclude that energy is simply lost. The gain of energy in quantum mechanics is hidden by a process called renormalization, which I'll describe in a moment. However, renormalization is just a trick to get your mathematics to come out right. There's nothing really physical about it. One can think of the situation as a sink filled with water entering the sink at the spigot and exiting the sink at the drain. The local level of the spigot is akin to quantum mechanical activity, where water representing energy is added to the system. Again, that borrowing of energy from the vacuum. The local level of the drain is akin to general relativity related activity, where water, again representing energy, is lost by the system. Because the amount of water leaving the system through the drain matches the amount of water entering the system through the spigot, the water level in the sink remains constant. You can think of it this way: water is not conserved at the local level of the spigot or the drain, but it is conserved globally within the sink. Now, if we look at general relativity only, we would observe the loss of energy over time. If you recall, when in general relativity, when matter is coupled to a gravitational field, the total energy vanishes. This diagram is just illustrating that using temporal energy theory concepts. If we look at quantum mechanics only, we can observe an accumulation of excess energy to the point of infinities. As I mentioned, some scientists use the mathematical trick of renormalization to get rid of the energy infinities on paper. One way is by using counter terms in the math to minus out the energy and leave only the amount you want. This is equivalent basically to just putting that excess water in a bucket and kind of throwing it out the window. Another form of renormalization involves something called the energy cutoff, which is basically like putting a curtain over the excess energy because it is not relevant to what you're trying to do. Neither of these solutions actually solves the problem. They just hide it from you on paper. They are mathematical tricks to glean meaningful results from your calculations. However, gravity does in a natural way what the mathematical trick of renormalization does unnaturally, in an unnatural way. When you involve both general relativity and quantum mechanics, the energy of the system naturally balances out. Quantum mechanics adds energy, general relativity takes it away. Thus, with general relativity, you don't need the renormalization techniques. Now, of course, you can use renormalization, but with the understanding that gravity is the physical process balancing the energy. Gravity then is focused on the T plus to T minus process. It is the time of Einstein. It is the time of general relativity. Electromagnetism and the weak and strong forces focus on T minus to T plus time. This is the time of Newton, the time of quantum mechanics. Thus, we can look at this from the standpoint of the problem of time. When you add general relativity and quantum mechanics, again, as you might recall, I said the time vanishes in the math. You get the Willard-Dewitt equation, which basically says there is no time in the universe. But viewing this from the standpoint of temporal energy theory concepts, you can understand why the Willard-Dewitt equation would occur. If gravity is focused on the T plus to T minus process, and quantum mechanics is focused on the T minus to T plus process, they naturally zero out. You can also look at this from the standpoint of energy. General relativity is focused on energy loss. Quantum mechanics is focused on energy gain. Again, when you add them together, they zero each other. Again, you can look at it from the standpoint of clocks. General relativity, that T plus to T minus process for all the matter in the universe is like a clockwise clock or clockwise time. Quantum mechanics, focusing on that T minus to T plus process, that opposite process, is sort of like a counterclockwise time. Again, adding clockwise time to counterclockwise time, you get zero. So really, there is no problem of time. Time should vanish from the math when general relativity and quantum mechanics are combined. The Willard-Dewitt equation with its time equals zero solution indeed provides the clearest and most complete picture of time in the universe. So then we ask, well, why do scientists, physicists feel that the Willard-Dewitt solution is a problem? Well, this is because I think many of them are viewing both general relativity and quantum mechanics as both forward-running clocks. If general relativity has clockwise time and quantum mechanics has clockwise time, you would expect a non-zero answer when you added them together. However, again, you get the Willard-Dewitt equation that says time equals zero. Thus, in this setting, the Willard-Dewitt equation would indeed be puzzling. It's like adding 1 + 1 and getting zero. Returning to the four-layered concept helps us to understand this too, particularly the bottom two forms of time, that time is a basic process, basic bidirectional process, and time is a thermodynamic unidirectional process. And now this is critical. Scientists today I don't think they recognize basic time. They believe all time as process time is thermodynamic time. The laws of quantum mechanics and general relativity are time symmetric. They do not give preferential treatment to backwards or forwards time. Thus, in my estimation, general relativity and quantum mechanics are using what I refer to in temporal energy theory as basic time, time that can indeed move backwards or forwards. The T plus to T minus process is just as legitimate as the T minus to T plus process. Neither one holds more importance. As I mentioned earlier, our universe would work just as well if it were composed of matter, of antimatter instead of matter, and focused on T minus to T plus time. However, because scientists do not recognize basic time, they tend to think that all time is thermodynamic time, which indeed has a definite directional arrow to it. Again, the fading of paint, the cracking of an egg, and so on. And assuming all time is thermodynamic time, when you add general relativity and quantum mechanics together, you are in a sense adding clockwise time to clockwise time. And again, you would expect a non-zero answer, making the Willard-Dewitt equation puzzling. But if you understand that the time of general relativity and quantum mechanics is basic time, it is easy to see why the Willard-Dewitt equation arises. Adding T plus to T minus to T minus to T plus leads to a canceling out of time and the result of zero in the end. And with that, general relativity and quantum mechanics are united. So, we've seen that the four fundamental forces of nature can be united through energy concepts. Gravity is associated with a loss of energy, and the electromagnetism, the weak and strong nuclear forces, are associated with a gain. Only together do they balance one another out. This together with the previous discussion about how time is relative and universal, helps us to see how general relativity can indeed be united, where the Willard-Dewitt equation is the best and simplest mathematical representation of that unification. With that, I'd like to move on to the subjects of dark matter and dark energy. The vast majority of the universe is composed of matter and energy that scientists cannot identify. They call this dark matter and dark energy. Dark matter composes approximately 20% or more of the energy content of our universe. Dark matter bodies can be very massive as well. Dark energy composes about 75%. The matter that makes up you and me and all the stars and galaxies really only accounts for about 4% of the matter. Now, recall also that I said that temporal particles are attracted to sources of energy, swarming and condensing around those sources. This means that temporal particles can be attracted to their own energy as well, forming clumps of time, some very massive, very large in space. These clumps of time are what I refer to as dark matter. As they do when they clump around planets, they curve and compress space. You'll get the effect called gravitational lensing when light from behind these masses, that light will bend according to the curves in space. But there's no planet. This is just time, clumps of time. Scientists have been trying to probe dark matter for some time, suggesting that it is composed of something called WIMPs, which stands for weakly interacting massive particles. But despite their efforts, they have not been able to understand what composes dark matter. In my opinion, it is simply because it is nothing more than space and time. Now, if we imagine two scientists, one on Earth and and another one who is going to travel to a huge dark matter body to examine it up close. Let's imagine that. And let's say the scientist can easily communicate with one another. The scientist on Earth says to her partner, you are right on top of the dark matter. What do you see? What's there? But the scientist in the vicinity of the dark matter looks around and sees nothing but what we would call the blackness of space. She says, there's nothing here. But her partner says, but you're right on top of it. But again, the scientist says, there's nothing here. In temporal energy theory, the discrepancy is caused by the fact that the two scientists are in two separate reference frames. Recall how different densities of temporal particles create different reference frames where time ticks at different rates. The two scientists are in two different reference frames. For the scientists near the dark matter body, there's nothing really out of the ordinary. But from the perspective of the scientists on Earth, the time of the scientists near the dark matter is moving more slowly. She also seems to be, she also seems to be more massive and physically smaller, not because she's far away. She literally looks smaller because space is compressed in that dark matter area. But to the scientists at the dark matter body, nothing appears out of the ordinary. She would notice that her colleague seems to be moving particularly fast compared to her, but she looks around and says nothing is out of the ordinary here. This is because the colleague on Earth is in a lower density of temporal particles than the scientists at the massive dark matter body. This is why she sees her partner on Earth. The partner on Earth seems to be moving a little faster because she's in a lower density of temporal particles. So that is what I believe that dark matter is. The dark matter, I believe, are just clumps of time, and therefore, when you probe them, there's nothing there. And that's why I think it's been so difficult to understand what composes them, because it's really nothing more than time when you understand that time has energy. This naturally suggests that the field of T plus particles filling space is dark energy, or what is sometimes called the 0 point energy of the vacuum. Now, again, as you might already know, space-time is expanding. Thus, as temporal particles are attracted to all forms of energy, they will be attracted to the energy of expanding space as well. In so doing, dark matter will behave like an anti-gravitational force. In my work, it is really, let me go to the next slide here. In my work, it is exterior space that is actually, I believe it's really exterior space that's actively expanding, responding to the repulsion it feels for the T plus energy that it's expelling into green space. As exterior space expands, it pulls interior space along for the ride. So the yellow space is really actively expanding, responding to that repulsion it's feeling for T plus, and it's pulling green space along for the ride. As interior space expands, the green space, some of the T plus particles, in a sense, chase after that activity, causing them to move away from one another, which again is that anti-gravitational effect. Now here, I added a dark matter cluster to show the difference. With the dark matter, the temporal particles are moving together under a normal gravitational effect. The arrows all the temporal particles are clumping as they would around a planet, as they would forming dark matter, a normal gravitational effect. But the temporal particles responding to expanding space are kind of, in a sense, chasing after that expansion and moving away, creating an anti-gravitational effect. So this is how I believe that what constitutes dark matter and dark energy. And this is the way I describe them in temporal energy theory. With that, I'd like to return to the concept of mass. As I mentioned before, dark matter bodies can be very massive objects, but they are nothing but clumps of time. So time is bestowing mass on the dark matter bodies. I like to suggest really that all mass is temporal energy. Here, temporal particles are responding to the naked energy of an electron and form an energy shell around it that we identify as its mass. But in the same way, but it is the same energy that exists in the gravitational field. I would like to also note that gravity appears to occur through the mass field, where an electron transforms a T plus particle of its mass field into T minus, and that T minus is absorbed by exterior space. And another T plus particle moves into the mass field such that the mass appears unchanging in time, but is actually turning over all the time. So this is how I describe mass, mass in general, mass of a dark matter body, mass of an electron, mass is really of anything. But how does the standard model generally describe mass generation? In the standard model, a bare electron is surrounded by what's called a Higgs field. As the electron moves through space, it interacts with the Higgs field. This interaction gives the electron mass and slows its movement. I want to emphasize here that the gray circles, the H's in them, are not Higgs particles. They are just simply there to represent the Higgs field generally. A Higgs boson would be a ripple or clumping of this field. Now, you might already be thinking this, but in many ways, the field of temporal particles throughout space in my work is very much like a Higgs field. Indeed, the time dimension, gravitational field, Higgs field, field of dark energy, and the vacuum energy are all the same thing when you understand that time has energy. They are the time dimension of general relativity. I want to stress again that I'm not talking about a substance in space-time. I'm talking about time as a component. Excuse me, I'm talking about time as a component of space-time itself, with these different fields representing that time dimension playing different roles. So the time dimension, the gravitational field, the Higgs field, dark energy, vacuum energy, these are all the same thing. They are the time dimension of general relativity, playing different roles. Now, in my work, a Higgs boson then is like dark matter. It is just a clumping, if you will, of temporal energy, but on a small scale. I place the electron and positron in this picture simply to indicate that we're on a small scale here. But again, remember that temporal particles are considerably smaller than electrons. Looking at the standard model mechanism for generating a Higgs boson side by side with mine, you can see that again, they are in many ways saying the same thing. So the electron, certainly it's saying the same thing in terms of a Higgs boson. So this kind of clumping of this field. I call it the temporal field. They're calling it the Higgs field. I say the temporal field and the Higgs boson are really the same. The laboratories at the research facility called Cern, which is based in Geneva, with the facility sitting astride the Franco-Swiss border, announced back in 2012 that they found the Higgs boson in their experiments. They discovered the Higgs boson. Now, their Higgs boson can decay into standard model particles like photons, electrons, and quarks. But mine, being composed of just time, temporal energy, really cannot decay that way. So how do we evaluate this discrepancy, right? Which one is the right Higgs boson? Is the Higgs boson that CERN found, right? Or is this, supposed Higgs boson, Lamont, that you're suggesting, is that a real Higgs boson? So one way to look at, to evaluate this discrepancy is to look at CERN's decay channels. Now, CERN's Higgs boson is said to decay according to 5 principal channels: the bottom quark and tau particle channel, the photon W boson and Z boson channels. The bottom quark and the tau particle channels represent the fermion channels, and the photon W boson and Z boson represent the boson channels. The signal strength is the rate of the observed decay over that which you would expect based on your theory. If the observed rate of decay matches that which you would expect, you would get a 1. So ideally, all the signal strength values should be a 1, such that the ratio of the combined signal strength of the fermion channel to the combined signal strength of the boson channel should be a 1. 1 over 1 is 1. So if the Higgs boson is truly the standard model boson, really all of these values should be 1. However, in my work suggests that for CERN's particle, the ratio of the combined signal strength for the fermion channels to the combined signal strength of the boson channel should really be about 0.83. Now, it might range from anywhere from 0.7 to 0.9, but generally speaking, around about 0.83. Now, unfortunately, I don't have time to go through the details of why this is, but temporal energy theory does dictate that CERN's results should be about 0.83. Now, when you look at the data, you do seem to see evidence of this. These are combined data from the 2 principal laboratories at CERN called ATLAS and CMS, published in the Journal of High Energy Physics. As you can see, the ratio of the combined signal strength of the fermion channels to the combined signal strength of the boson channel is about 0.8. It's about 0.77, about 0.8. Here are some more data from different studies. The top one is the one we just saw. The next one at 0.78, that's the ATLAS data from the same study, but just looking at the ATLAS data by itself. The top one was ATLAS plus CMS combined. The next one is from that same study with just ATLAS data alone. That one came into about 0.78. The CMS data, again, from that same study, but just looking at the CMS data only, that one indeed came out to about 0.83. CMS published another study where that ratio came out to be about 0.91. And then there was another study by ATLAS, which came out to be about 0.93. Now, in that last study, there were 2 outlier data points that I removed: the bottom quark value of 3.0 and the Z boson of 2.68. This is because they're far even above what the standard model would predict. If it were a standard model, you would get a 1, and these values were so far even away from 1. When you account for that, you take those out, you do find about 0.93. Altogether, they average out about 0.84, which is close to what I would say that they should be. Now, another problem is that Cern's Higgs boson should have a range of mass values. It should range from anywhere from 100 to 1,000 giga-electron volts or more, but consistently is observed to have a mass of about 125 giga-electron volts. Now, my Higgs boson can indeed have a range of mass values. As you see here, so similar to dark matter, they can be almost any probably range of values. So really, my Higgs boson is consistent in that way, in that it can be a range of mass values, very something very small to very heavy. So if you want to compare Cern's Higgs boson to or Cern's results to Higgs temporal energy theory's results, we see that the Cern Higgs boson can decay into standard model particles, but my Higgs boson is not capable of decaying into standard model particles, being just a clump of time. However, the combined fermion to combined signal strength for Cern's particle should be a 1, but it's not. My work can demonstrate why Cern's particle leads to a value of 0.83, as the data seems to suggest, at least so far. Cern's particle, if it is a standard model particle, should have a range of mass values, but it doesn't. It has one value they keep finding consistently, 125 giga-electron volts. However, my work, a Higgs boson would have a range of mass values. So in some ways, temporal energy theory's Higgs boson is actually a little more consistent, not completely, but a little more consistent with the standard model Higgs boson. And it can also help explain why Cern gets some of the findings that it does for its particle. From the standpoint of my work, temporal energy theory, Cern's particle is really just an exotic standard model-like particle that decays in a particular way. I can model it, and I just unfortunately just don't have time to do it here because it takes a little. It's not complicated; it just takes a lot of steps to explain it. But it's really not that complicated, and you can see why you get that 0.83 value very easily when you examine how that exotic particle would decay. Unfortunately, the scientists at Cern do not typically provide the ratio of the combined signal strength of the fermion channels to the combined signal strength of the boson channels. They often just take the average signal strength among all the values. And when you do that, you can almost force, I won't say force, but the data kind of do get to be about 1. When you just take them as one lump sum, you can kind of get the data come out to be a 1 collectively. Because honestly, I have not seen any data from Atlas or Cern where all of those channels are 1. Because remember, all of those channels should be 1 individually. But I have yet to see any of those data come out to just be a 1. There's sometimes they're higher than 1, sometimes they're lower than 1. But typically they combine all of them and they say, well, the combined signal strength is 1, and therefore it's consistent with the standard model. However, I do believe if they broke their data down as previously shown, they might indeed see that 0.83 result. Or again, it might be anywhere from 0.7 to 0.9 roughly. So the way I look at it, Cern is doing tremendous work, but I really think that they are touching the theory of everything more than they are Higgs boson physics. So hopefully they'll see this video and maybe they can, evaluate that. So I want to turn to our final 2 questions. Can any of this really help us to be a multiplanetary interstellar species? And what's the connection to thought and the mind? So we are swimming in energy. Energy is all around us, but the question is, can we tap into it to do useful work? To do work, you need some sort of energy difference, like gravitational potential energy being used as water flows downhill to run a generator. Temporal particles are moving throughout space, and therefore they are creating currents. However, this is really just gravitational potential energy, really. Like, that circle could be a planet, and all of that energy is just gravitational potential energy. However, these currents are going on in the outer reaches of space too. If you recognize that there are particles out there that are moving, not just this kind of smooth, continuous dimension that Einstein says time is, but if you recognize it as really a lot of active activity, really a lot of activity related to the movement of temporal particles, you'll find there's a lot of temporal particle currents in the far reaches, outer reaches of space too, as these temporal particles move about. So the question is, can we tap into those currents to do any useful work? You know, that's just a question. We'd have to see. Now, this diagram shows the flow of temporal particles between exterior space and interior space. And if you think, and it's understandable if you think it looks familiar, and not just because of what we just discussed, this is because it resembles a battery setup, where exterior space is the battery, it's like the battery. Matter is the device on which the battery is operating, and the flow of time is like the electrical current. You know, the question is, could we access the energy of this battery-like system that is the universe, particularly in the outer reaches of space, allowing, for example, better space travel, for example. So there's energy out there. Temporal particles are moving about. The entire universe resembles a battery setup, almost literally. So it's a question of what, you know, could we use that energy in any useful way? After all, we are not going to get to Mars on a tank of gas. And certainly there's the question of whether it could help us with our energy needs on Earth too. So I'd like to turn now to the concepts, some concepts about thought and the mind. This is Rene Descartes. He is famous for his saying, I'm sure you all know it, I think, therefore I am. I'd like to suggest that our first thought really is about time. It is an inherent understanding that this moment is somehow different from the one before. And it's what we know first and what is the foundation, I believe, of self-awareness. The link to the different forms of time is clear. The time dimension, you drill down, you find a time particle. That time particle can engage in basic time, the time of electrons. The electrons, in a sense, gain energy from that, allowing them to wiggle and jiggle and radiate electromagnetic fields in one direction, with photons traveling in that one direction, leading to a unidirectional flow of time, that thermodynamic flow of time. And certainly that thermodynamic flow of time is really the basis of our psychological time. You know, a melting ice cube doesn't spontaneously refreeze. A cracked egg, you know, doesn't spontaneously reform. That gives us a sense of psychological time. But I'd like to suggest that, you know, I think even probably on some very, 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 very basic level, I think that we potentially even have a sense of basic time. It's really that heartbeat of an electron, that pulsing energy as it takes in a T+ particle, transforms into a T- particle. And it's because it's those electrons that are composing our brains. So I believe, or at least, you know, just kind of, it wouldn't seem unusual that on some very maybe basic primitive level, I think we have an innate sense of this energy change going on with inside of ourselves. So I'd like to begin to close with a few statements from my book. The greatest source of energy is time. As a physical object, time is an energy field that spans the cosmos. It surrounds us and penetrates us and binds everything and everyone together. Time gives the universe substance. It gives mass to matter. Time is the solid ground under our feet, the clothes on our backs, the food we eat, our skin and bones, and the sunlight that shines on us. As a process, time sustains us. It is the breath of life of every rock, tree, and creature, every electron, every particle of matter. Through time, everything lives and everything is connected. And I'd like to add that time is the root not only of the physical world, but the mental world as well. It is the content of our very first thought and what gives us a sense of self-awareness. So why does it all matter? I think because it is critical that we better understand energy and how the universe works for our long-term survival as a species. And I also think it's important to better understand ourselves. A question we might ask is, is there an evolutionary step we can take as we better understand our connection to the universe, both physically and mentally? Perhaps. So we return now to our friend St. Augustine, who asked, "What is time?" And I think we can hopefully answer maybe that question now. So time is a four-layered concept. It is a dimension, a field of energy that permeates all of space. As you drill down, again, you get that time particle, that T plus particle filling our space. It is a bidirectional process where T plus can be converted to T minus, where that process is just as legitimate as a T minus to T plus process. And it is a unidirectional process where thermodynamic events happen in one direction. So if temporal energy theory is proven to be correct, it cannot be regarded as a theory made from scratch. Rather, it is an extension of past ideas dealing with the forces of nature. Isaac Newton provided many profound and lasting thoughts on gravity. Albert Einstein followed up on Newton's thoughts, providing a more precise description of gravity and general relativity. And he laid the foundation of quantum mechanics along with a long list of distinguished scientists for describing electromagnetism and the nuclear forces. Temporal energy theory is an endeavor to combine general relativity and quantum mechanics, and thus the forces they describe, picking up from points where the other theories leave off. Much more study is needed, but I hope the information provided here will be useful, and I hope it's interesting. So I'd like to say, once again, that Isaac Newton and Albert Einstein are both right. Time is universal and relative. These are not incompatible concepts when you understand that they are both happening in the universe at the same time. So with that, I'll just close with, my website is www.greatestsourceofenergy.com. You can follow me on social media. I'm not really good with social media. I am going to be posting more on social media in time, but you can sign up on mailing lists and hopefully just follow along. There's a nice video of the introducing the book on YouTube. It's a little under 2 minutes. You can just put in Greatest Source of Energy and Lamont Williams. It'll come up, or just follow that URL. You can contact me at williams_lamont@outlook.com or through my website, greatestsourceofenergy.com. I'd like to thank my artists. Any nice looking art is theirs. Anything that looked like a kindergartner did, it is mine. No offense to kindergartners. And again, I'd like to thank the Monterey Friends for having me, and I hope that this was interesting.
Thank you.
Thank you.
Right.
Wonderful.
Yeah, thank you. Okay.
You're welcome.
Let's go back into
Our friends,
gallery view so we can
see if anybody's got their hand raised.
see if there, first, any questions? Does anybody have any?
Just something came to mind right at the end.
Yeah.
Okay, if time is a particle, then are you saying that thoughts are things?
Well, I think that's something we can explore. I think that is something that the connection between temporal energy, temporal particles, and time and thought is something that I think is ripe for exploration.
So, first of all, I want to thank you, Lamont, because I was really kind of struggling to put everything together as I read the book, and you just did a beautiful job putting it all together here for us.
Thank you.
So I really appreciate that, and I think I'm starting to get it, and a few other little tidbits of information that I've heard, over the years, kind of started floating in, and like finding its fit within this theory, like about 15 years ago, mathematician physicist was explaining to me how some particles, like they have a certain spin and they pop out of our reality, and then when they pop back in, they have the opposite spin. And your notion of exterior space, kind of like, oh, maybe that's where they're popping to. And this conversion from T plus to T minus and T minus to T plus might have something to do with the, the spin flipping. And I went into 0 point energy in my novel, but I won't get into that tonight. But I have some thoughts about 0 point energy, and I really liked your the metaphor of the circuit to help contextualize all of this. But I'm going to shut up because Eileen has her hand up. Go ahead, Eileen.
Well, I did some listening to various people on time this week, and it seems as though you're in the minority of people who think that actually time does not exist. The majority think that time does not exist it as a fundamental part of nature, that it's an emergent phenomenon that is an illusion. But on the other side, there are two eminent people, and that's Sean Carroll and Lee Smolin. They didn't mention, or I don't think that's part of their of their idea of time particles. But I wonder what you think of them. Lee Smolin thinks that time is something evolutionary. But okay, that's one part of the question. The other part, it's when you have an exterior universe, it's like having a multiverse. How is one ever going to get the data, the experimental data? How could one get, which ultimately you have to get the experimental data. And let's see, there was one more that what I really liked was this beautiful simplicity, the idea that everything is symmetrical, relatively simple, that it's not a kludge work that you have, that it all unfolds in the negative positive, and it makes nature seem reasonable, as opposed to right now that it seems that physics is at a sort of an impasse, waiting for something to somehow knot this whole sludge work together. So those are my thoughts.
I really appreciate that, and I appreciate recognize it. There is a certain symmetricalness, right, to the work, to my work, and simplicity to it, which I can appreciate too. I think the problem for your first question, I think it has to do with not understanding that there is this thing called basic time, right? All time is not thermodynamic time, because I think it's that trying to fit the thermodynamic square into a hole that's really meant for basic time. And so when you try to do that, I think you get all kinds of flutterings of thoughts, and I think that's probably what leads someone to might think very thoughts about time that really aren't necessary, like, oh, doesn't it really exist, or it's an emergent property or something like that, because they're missing a piece of the puzzle, or they're trying to put the wrong piece in the wrong slot. So I think all those kind of machinations kind of create all kinds of distortions that really aren't necessary when it comes to understanding time better. Again, I like what you said. There's a simplicity to it. If you understand all the pieces, they all fit together. You know, you can imagine if you're missing a piece of a puzzle and you're trying to jam fit a wrong piece in a spot, you know, you're going to get these distortions on your puzzle, and it's not going to look right. And I think that's part of the problem why we get all these kind of, I think, unnecessary kind of wild ideas sometimes about time. When it comes to measuring this, I think it's really already done. For instance, of like regard to exterior space and the activity of exterior space, it's quantum mechanics. We can't know we can't measure it, but we can measure the energy that comes from it. They know that energy is coming from somewhere. It's part of the fabric of quantum mechanics itself. They just say it's coming from the vacuum somewhere out there. Now I just dig a little deeper and you know, connect it to a lot of different other concepts. But really that work of exterior space is really already done in a sense that it's quantum mechanics. Because also you might recall it's really, exterior space is actually the same thing as the negative energy vacuum of quantum mechanics. It's the same thing. It's, you know, my work, it's filled with T minus, and that's why it has negative energy. But again, I'm looking at it at a layer down than I think most people in the field of quantum mechanics are doing. So I hope that answers your question.
Are any people following along on that time as being primary? Are you an outlier, or are there other people working in that same focus, starting from time?
I'm not sure. I can't say. I have not seen anybody who's thinking the same things that I'm thinking, to be honest. You know, I guess that answers your question. No, I have not seen anyone really relate time to a particle. You know, I think also there's this Einstein's time as this smooth dimension, right? The smoothness of the space-time, I think also kind of distorts it. Really, another way of thinking about it is like, you think of like the smooth surface of water, right? But you can drill down into water and find a molecule, right? It's particulate. And I believe that the time dimension itself is a particle there, but no, not many. I have not seen anyone who's thought along those lines, to be honest. Spread the word. Spread the word.
So you know, when I look at this, I see an analogy with what you're doing with string theory, for instance, where the strings could be analogous to the temporal particles.
That's an interesting. I had never thought. I have not heard about string theory. Seem to have fallen off the radar.
Well, it primarily is because it's not testable. So I mean, that's the primary reason. But it was just thinking along those lines, and then I was thinking the second thought: is there anything at this point that's testable in your theory?
Yeah, the Higgs particle decay. I actually, it's funny. I actually predicted that 0.83, but I didn't publish it anyway. It was actually an email to a physicist I had been communicating with, and I said, you know, when it was first coming out, I said, you know, I think this ratio should be about 0.83, and it was before there were any data out, and then it did come out, and he said, oh, maybe you're onto something, you know. So I wish I had been a little more forthright about that at the time. Yeah. But I can, and unfortunately it takes a bit of explaining, but I can at least show in my work why it would happen. And if Cern would do that data, do the combined fermion to the combined boson, I believe they would continually find that 0.78 range of values, and that is what I'm saying alone out here in the world. That I don't think there's anybody else saying that's a real thing. It should be about 0.83. Now the reason the particle experiments are a little fuzzy, and that's why it's hard to look at the individual channels all the time. So they kind of, so that's why I because really in my work, the tau channel, the bottom quark should be like literally 8.83, and then the other ones should be a 1. Now, the numbers get they just kind of get a little fuzzy just because of the nature of experiments. So I think it's the cleaner examination is to look at the combined fermion strength divided by the combined boson strength. That seems to come out a little more cleaner, and it should be about 0.83.
Yeah.
And I can explain why.
Well, I'd like to know what the error budget's on there, where what makes sense, to look at this point, as the energy is increased in the Large Hadron Collider, then that error budgets will get smaller, I think.
Yeah, they're pretty big right now. Some of the ones I've seen are the errors are pretty large, depending on what you're looking at. I think they're still struggling with the bottom quark, and I believe the tau sometimes, but I think some of the boson ones are coming out pretty nicely, but it's not all fitting the way they would think that it would fit. But I think I know why. So but that's me.
Okay, that's a good place to look. Anyway, yep. Okay.
So I have just a basic question and then a follow-up. But when you're using the term time particles, is this a metaphor? I mean, you're not using, or are you using particle in the same sense of when we're talking about light as being both wave and particle? Are you using the word particle in that sense?
Yes, when I literally mean a particle. It's a small, almost. You probably know the Planck units. It's like a Planck size. It's tiny. It's a part.
Yeah.
So I think what actually happens is when the universe is created, as it expands, it creates a true vacuum, and a true vacuum is really unstable. I believe it creates a temporal particle to bring the energy down to zero. It actually creates temporal particles it's kind of an opposite process, but it creates temporal, because a true vacuum is a higher energy state. So I think the temporal particles are created actually to lower the energy, and then they fill all of a space as it expands.
That's interesting, because as we think about the origin of the universe, right at the beginning, nothing can form, or something cannot come out of that in the beginning, because the energies are way too high. So what is that? And the temporal particles would make sense from having this soup that is what? Energy. So it was that's my thinking on that when you're just talking about it there.
I can say, yeah.
So is that your thinking too?
Well, the way I look at it, I talk about the universe being that sort of what I call seed of green space, electrically neutral. I believe it's just sitting on a razor thin edge of its blue and yellow nature. It's yellow and green, or electrical negative and positive charge, which is a very precarious symmetry. And I think that any small change, any small vibration or change will make it polarize, and just you get that kind of boom and that polarization of the space into its blue and yellow, or negative and positive, and then it just starts this almost massive reaction. So I don't know if that answers your question.
No, I was just wondering what your thoughts were on that. That's
I want to ask one more question, and that is, in the modeling you had psychological time and so forth, but I'm curious as to how you might describe consciousness as a property of that in this model, emergent or otherwise. Does consciousness, how does consciousness happen in your model?
John, that's enough for a whole nother lecture.
Yeah,
And
I purpose. Yeah, go ahead. I'm sorry.
does consciousness, assuming we can use the word, does consciousness increase, which would imply a time factor? And just how would you plug all that in?
You know, that is reason I focused on self-awareness as opposed to consciousness. I can't speak to consciousness. I can speak to, you can be self-aware even in your sleep. You can be unconscious, you can be unconscious and self-aware. I thought that was the easier thing to talk about. Consciousness, that is a tough subject. What is consciousness? But that understanding that, what I say, this moment, this abstract this moment is somehow different from that moment, the one that just happened. That understanding, I think, it gives you a sense of self-awareness because you're understanding something has changed. And I believe, like I said, I think maybe we have some sense of that energy change, that like I said, that pulsing of changing of energy, even on an electron scale, that particle scale, where that there's because there's just this constant pulsing or changing of energy as T plus comes into contact with an electron, T minus leaves. We might have a sense of that, but that's again, that's more self-awareness. Consciousness, I couldn't really touch that right now.
Yeah, Eileen, go ahead.
I was thinking that the way you have described time as a particle makes it different from other descriptions of other particles, because they're usually described as particles and waves. And so you've got an isolated particle, so that already makes it something different and special. And then you also have what you said, you have a sense of change. So you have a sense of an arrow of time. So that's two very extraordinary different things from every other particle wave. Does that bother you, or that you don't have this symmetry with other fields and particles?
No, it doesn't. And the reason is because my temporal particle is really just a drilling down into the standard quantum mechanical particles. So a temporal particle will create the mass shell of an electron. It's actually also involved in the energy waves of light and so forth. So you might even say then that particle wave nature, that is an emergent property.
Yeah, I see. So time is the most fundamental of the fundamentals.
Yeah, I do believe that.
Yes, I see.
We had on a guy a couple weeks, well, probably a month ago now, who is writing a series of science fiction books, and he takes on the notion, in the question of will we become an interplanetary or intergalactic species, and in order to do that, the distances, the travel distances are just prohibitive. So his trick, instead of like warp drive, his trick was a temporal reduction. So you'd to travel these great planetary distances as an interstellar species, one would have to like change one's internal clock change time. It was like, you know, you'd have to like fiddle with the time dial. And I don't know, I think maybe you'd enjoy his fiction.
Yeah, I'd love if you could, send me that information. It
Yeah,
sounds similar. It sounds like he's touching on what I'm kind of touching, that it's really, it's really the answers in time. And even Einstein is really emphasized, even gravity. Gravity is his way, the curvature. He says curvature, but curvature of time. Space really doesn't have, this curvature of space doesn't really have a lot to do with gravity. It's really the curvature of time. It's just that the curvature of space is just there because it's along for the ride. You know, space is curved, time is curved, time is curved, space is curved. But it's really about time. And I think time is the root of a lot of things that really that's going to take us to the next level, just as the author you're referring to is suggesting.
Oh, another thing that I was thinking was the importance of perspective in your work. And I read a philosopher by the name of Hugh Price who talked about causality in terms of perspective. So I'll send you that too. I think you might enjoy it.
I'd love to. Yeah, I think there's so many ways to look at the work that I've done. You can just focus on time. You know, you can focus on the combination of general relativity and quantum mechanics. You can focus on relative versus universal. And so there's so many different ways of looking at this. So that's one of the things I think is I find interesting. But it's multi-dimensional, if you will, in that sense.
Yeah, it's very much both and. You know, so many people are stuck in the paradigm of it's got to be either or. It's got to be relative or it's got to be universal. And to be able to pull them together in a both and sort of way, I think is you know the way we have to go.
Yeah, I think I really wish that a lot of people knew that you know Einstein and Newton are not incompatible at all. Not at all. But it's so often, it's still like to this day, I think in mainstream, it's like either or, is either or. And it really doesn't have to be that way. They are both right. They're both there you know, in the universe in just different ways. They're just two processes going on, one in our space and one in a parallel space, but that parallel space affects our space in terms of that borrowing of energy that quantum mechanics uses. That is that other time process. Not all time is thermodynamic time. So there's a basic form. You know, because sometimes you know, I'll watch videos and they talk about how time symmetric general relativity and quantum mechanics are, and then in so doing, they'll use thermodynamic time. They'll say, well, the laws of physics, you know, can go either way, and then they'll try to, you know, run a clock backwards of an egg going back, you know, or an ice cube, you know, like, well, physics says, but then, you know, well, obviously logically that doesn't make any sense, and then it gets really confusing in terms of what they're trying to explain. But it's really not understanding that there's a basic time that can go in both directions. But that's a little different than thermodynamic time, which is one directional. But if you don't understand that general relativity and quantum mechanics are focused on basic time, it gets, you know, things get a little muddy.
I was going to ask, since a time particle is a Planck constant particle, it's
Planck
the
size,
smallest thing that we can not just imagine, but then say it exists. It's at 10 to minus 35 meters. So the idea of isolating it like in a super collider is beyond the pale. Is that correct? Like you would not get clumps of time that you could possibly think could be isolated in a collider.
No, you could not. You could never do that. And no, not at all.
So it would all be inferential. What the evidence that you have, like what you have already, and what you would envision in the future would be inferential.
Yeah, yeah. You could never use it like a particle collider to find
Right,
a temporal particle.
right,
They're just too tiny. They're just too tiny.
right.
I actually think that they're involved in, the double slit experiment, where you
Yeah,
send two electrons through. So
yeah.
remember, I say temporal particles are attracted to all forms of energy. So if, the idea is that if you put a detector at one of the, I'm sure you all know this, you put a detector at one of the slots, the interference pattern disappears. But a detector is it has energy. It is an energy source. So I believe temporal particles will gather around, if you will, or converge on that energy source and distort the interference pattern. And if you don't have that energy source there, you will get the interference pattern. But I think it's it's really that convergence of temporal particles around that energy source that is the detector that
Mhm.
breaks the interference pattern.
Well, nobody's mentioned the idea of the exterior space as the collective unconscious. So in the last 10 minutes here, I'm gonna throw it out to our Jungians.
It's everywhere, right? It spans the entire, the entirety of our space. So, hey, maybe.
Yeah, and the implicate order, we'll throw that one in there too.
How would that work? How would that work? How
I don't
would that?
know.
You have to relate it to.
Well, I really, like I think, and I'm not saying my work is all right. There's a lot more that needs to be studied and evaluated, even about what I've done. I just try to offer some thoughts, offer some what I hope could be solutions or potential solutions to some really um, long-lasting problems, and just a different way of thinking about things. It is interesting to see, some struggles that I see on, some shows or some, different programs struggling to understand time and connect time and general relativity. And I look and say, they only just kind of looked at it this way, everything would work out fine. I really like what Eileen said, it's the simplicity, it's the symmetry of what I'm putting out there. It's really, it all just kind of fits together very, very nicely. And it doesn't lead you into very wild things. And so, but anyway, hopefully in time, I mean, like I said, I don't know that I'm right. I don't know that I'm right. So we'll have to see. But hopefully some people will take a look.
It's good food for thought. It's because we have to think differently, and we're so far we haven't thought in the right direction yet.
Right.
Either there's something about the way we think about general relativity that is not quite the right way to think about it. And the same thing with quantum mechanics. There's something that we are overlooking. And you're providing us with a possible solution to that, a different way of thinking, and that's very valuable.
I appreciate that. I appreciate it.
Yeah.
I love the little sink image, right? The little spigot and the drain, right? Quantum mechanics is the spigot, general relativity is the drain. There's a conservation of energy within the sink, conservation of water in the sink. One adds energy of water, one takes it away. Again, back to what Eileen said, that simple symmetry is, I think that's an image that it's helpful.
Yeah.
Washing up won't be the same.
Right. It'll never be the same again. It'll never be the same again. You'll never look at a sink
Yeah.
same again.
Well, and from there, so you can build on that. So that model is it's a model of a simple system okay? And then we get into complex systems, or complicated systems and complex systems. And, you know, but we both in physics, we start with simple systems, and in systems theory, we start with simple systems in order to better understand the complicated and then the complex systems.
Exactly. You know what? You triggered a thought. One of the reasons that I believe that physicists are having trouble with all of this is because in order to do the work that I do, you have to think like a biologist, not a physicist.
Yeah.
I studied biology. That's why I talk about suffocation and breathing. You know, physicists don't think like biologists. You can't come through any serious study of biology without an appreciation of the concept of a cycle. You know, biology is filled with cycles, right? The life cycle, the Krebs cycle, all cycle. You know, but physicists aren't used to thinking that way. And well, I mean, you know, there's astronomical cycles, but I think particle physicists, I don't think they think about cycles in quite the same way that a biologist would think about it. And I think that it's that biological perspective that really helps you to see the physics problem differently. That's why I often, you know, even in the book, I talk about temporal respiration. I talk about breathing. I talk about the breath of life, the pulsing of an electron, the heartbeat of an electron in a certain sense. There's a biological way of thinking about it that I think really at least gives me, at least I hope, some insight into, you know, how these things all fit together. It's almost like a biological system in some ways.
It makes me think that you should look into Lee Smollen's work, because he took a biological stance. He combined evolutionary theory. He was going in that way, and then he found as a physicist, he didn't know much about biology, and then he found biology and applied it to his work. And so that's why he came up with this evolutionary basis of time, that it's one particular time on our current stand, but elsewhere in the cosmos, there'll be different times with different fundamental equations based on the fundament, which is a different time. So it makes sense to him that the equations, the basic equations of physics, are not, he calls them not rational, they're not clean, they're not pure. And he uses the idea of evolution to explain why there would be maybe different variations of time, different variations of physical laws. And he's quite well known for his he also combines with Carl Rovelli with the idea of quantum loop gravity.
Yeah,
So,
loop quantum gravity. Yeah, I didn't know about that evolutionary part. Go ahead.
The last idea I'd like to throw out is, you know, when I was learning Chinese philosophy back in college, one of the things that we learned was that the Chinese had a bidirectional concept of time. Now, I'm pretty sure that just meant at the macrocosmic level, you know, like they would rebury their ancestors in order to affect their ancestors' lives. You know, so what you do today had an impact on the past.
Wow.
In Chinese cosmology. So it would be interesting to see whether, you know, that notion of time, you know, the bidirectionality of it anyway, not just in the Wheeler Dewitt sense, but in, you know, in the general sense, like you developed, was sort of like in a nascent state in ancient Chinese philosophy?
Yeah, I think we have some sort of deep understanding of all of these things, on some deep level, that maybe we're not fully conscious of, but but it percolates, right? And it comes and it manifests in different, like, different philosophies about life, or in the case that you were just describing. Um, and it's interesting also, when I realized that in my work, the Big Bang is like a let there be a let there be light moment, which I didn't see coming. I just kind of it's just kind of like, oh wow, it's like the whole universe is like a particle of light. That's the Big Bang, at least from my work. Um, I think deep down inside, all of these civilizations, all of humanity, we have a sense of a lot of these things, and we may not have all the knowledge to put it all together. But I think we have a sense of it, and I think it manifests in maybe, the stories, or the beliefs.
Consciousness.
Yeah, exactly. And yeah, exactly. Exactly. Right.
All right, well, we do like to be cognizant of time.
So to speak, right?
So I want to thank you very much, Lamont, for doing this. We really enjoyed it, and this was a great discussion.
Thank you.
Thank
Yeah, so we'll put this up on YouTube, and
Yeah.
you can link to it.
Sure.
I know I'm going to watch it again.
Okay. I hope I didn't speak. I hope I didn't. I was a little nervous in the beginning. I hope I didn't say something, say something opposite of what I meant. But yeah, I'm sure it's fine. So yeah, but please do share, and I really thank you for having me, and giving me a forum for these thoughts, and really all of the programs that you have are wonderful, and really leave you with good food for thought. So I really applaud you all for what you do.
And thank you for staying up late.
Oh, I'm a night owl. I'm a night owl by nature, so this is nothing for me.
Okay.
This is nothing for me. But thank you again. I really appreciate it.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Bye-bye.
Thank you. Take care. Bye-bye. Thank you.
Bye-bye.
Bye-bye. Well, David,